Good afternoon, everyone. My name is Armando Juarez, and today I will be presenting a paper. The paper is titled Secure Page Fusion with VUsion by Marco Oliverio, Cavarazzavi, Herbert Boss, and Cristiano Gufrida. We'll jump right into it. First off, what is page fusion? Well, page fusion, at a very high level, is essentially just the fusion of homogeneous pages for better memory storage. A little more in depth, closer to the weeds, is when a duplicate page is found, only one copy is kept, and all the page table entries of sharing locations point to the copy without the right permission set. This is the fusion end. The duplicates can then be returned to the system, and at any point, one party may decide to write to the fused page, which then will create a page fault. The page fusion system will reflect correct behavior by performing a copy on write and allocating a new page with the shared contents before updating the page table entry. Next, we're going to talk a little bit about how page fusion is vulnerable. There are two classes of attacks on page fusion: information disclosure and physical memory massaging. The first pertains to the slow unmerging, which allows for detection of copies. Physical memory massaging is a little bit more in depth. It deals with corrupting data via the DRAM bit flip. We'll talk a little bit more about what these are here in a moment. Next is, what are the design principles that this paper has presented on how they can secure page fusion? And they are as follows. First is enforcing same behavior, SB, for all pages. Basically, this comes down to removing access while merge decisions are made, whether it's a candidate for being merged or if they're just simply scanning it. Next is randomized allocation, RA. The idea here is you need to allocate a random page for backing and a candidate page for merging. And a candidate page in this case is a page that has been seen to be potentially fused but has yet to actually gone through the scanning to confirm whether or not there is another homogeneous page to it for them to be merged. And so we're going to talk a little bit more about the current page fusion implementations. First, in the Linux kernel. The Linux kernel has same page merging, is what they call it, KSM. It's opt-in and requires the use of the madvice syscall. Something else that uses the KSM is actually KVM, the kernel virtual machine. So first, it starts with scanning. The KSM will locate all virtual memory areas, VMA. It adds them to a candidate VMA list for fusion, and then the KSM will round robin through it and begin actual fusion. A virtual memory area is a contiguous area of virtual memory and pages that belong to the same VMA with shared properties. And so to talk a little bit more about how that actually works in the context of this paper, we have this. It's a little step-by-step on how it works. KSM underneath the hood utilizes red-black trees, hence the colors and the figures. First, each page is scanned and then checked with other pages to detect homogeny in the stable tree. If so, then the page is merged by updating the page table entry to point to the new location, and then write access is removed. If not, the KSM matches those pages against the unstable tree, as shown in the figure. If a match is found, the page is then made read-only and then moved to the stable tree. And then the match is removed from the unstable tree. If there is no match, then the page is put into the unstable tree. And it's these two balanced trees that the KSM utilizes underneath the hood in order to perform the actual fusions. And so the merging here implies that the physical memory of one of the pages is used for backing the shared copy. The figure here will reflect the different changes as seen by the blue GIC and those being candidates for being merged. Next, we have unmerging. The idea here is that there is one party that would like to write something to something that has already in that fused list. And so what happens is a copy on write event is triggered, and the reference count is dropped by 1. And if the count is 0, the system will remove the original page from the stable tree. This implies that as long as there is a single user on any file, then it will always be part of some tree available to be a candidate for Fusion. Now let's talk about Page Fusion in Windows. So it was on by default until the dedupe est machina attack, and it works by Page Fusion in Windows works by the following. In the scanning end, it scans all physical memory pages every 15 minutes for merging, and metadata is stored in AVL trees, and then a hash of the physical page candidate is computed, and then the AVL tree is sorted by those hashes. On the merging end, for each physical page, it first finds the process that owns it, and then inserts it into a tree sorted by the memory management structure pointer. Now let's talk a little bit of how the actual merging happens underneath the hood in Windows. But first, for each progress, examination of the contents of each page occurs. Then, if a page with the same content is fused, the WPF will find it in the AVL tree, and then the page table entry is updated, and then the physical page is returned back to the system. If the page has not been found, then the WPF will check for the same content. If so, copies are added to the AVL tree, updates are made, and returns back to the system. If not, then nothing is done. And then again, this still implies that the physical memory of one of the pages is used for backing the shared copy in the Windows format. Unmerging for Windows is extremely similar to the KSM. It just performs in the same fashion a copy on write after a change has been discovered. Now, let's next talk about the threat model that the paper has brought forth. The paper itself is presenting a new style of secure page fusion called VUsion, and so as a result, because they are incorporating some security, they have decided to add a threat model to what they are going to be defending against with respect to the vulnerabilities around page fusion. The first is an attacker can directly interact with page fusion by crafting memory pages with their chosen contents. Second is the attacker can trigger bit flips using the row hammer vulnerability, which will be discussed later, or other potentially exploitable reliability issues. And then the goals of the attacker is information disclosure and flip feng shui. Information disclosure would be in the form of abusing timing side channels induced by page fusion to detect fused pages in system and to disclose secrets. Flip feng shui abuses the physical memory massaging primitives that have been induced, and both of these will be discussed a little later on. And so they first wanted to talk about some known attack vectors as they have described in order to highlight the more aggressive weaknesses and vulnerabilities that they would like to protect against. Now, like described earlier, one of the classes is information disclosure. The premise of this class is that it is unmerge based, meaning it is when the pages are no longer fused, that it is during that time that they can exploit some kind of timing side channel in the copy on write. And what this allows them to do is it tells the attacker if a page exists on the system. And then can be taken further to create covert channels. It can be taken even further to create some kind of fingerprint based on how the system itself reflects and communicates with the different fusions and unmergings. An example of one is called the Kane attack. This one is a brute force style kind of attack, where it will create pointers of VMs that are randomized by the address space layout randomization, and then it will then watch via that timing side channel, the copy on write, to detect if one of those pointers actually goes to a virtual machine located on the system. This has a lot of potentially bad things that could happen, because now if one system can determine whether or not virtual machines are there, the sky becomes the limit with this next attack that is going to be discussed. Flip Feng Shui. Now, this one is a little different. It is merge based, and it exploits the physical memory massaging to land sensitive information in a vulnerable memory page and trigger hardware bit flips to corrupt it. Basically, this comes down to they are able to exploit how the pages themselves become merged to sort of funnel them into a piece of memory that is already vulnerable, for the purpose of triggering bit flips inside of that memory. And this one, the most famous one, as described by the paper, is the DRAM row hammer attack. It's an exploit on the fact that if two rows in DRAM are activated in succession many times, the residual charge leak can reliably flip bits from the perspective of the CPU. In layman's terms, essentially, there are these two rows inside of DRAM architecture. They're called aggressor rows. And if you continuously write memory to both of them in quick succession, then what ends up happening is the capacitor inside of one of the rows eventually will start to leak charge. And that leaked charge is enough to actually flip bits of the surrounding cells that hold those capacitors. And from the perspective of the CPU, it sees that bit go from 0 to 1 or 1 to 0. The possibilities that can be done here is Rowhammer can allow for someone to essentially flip the bits inside of a page table entry to perform some kind of privilege escalation. And once you have sudo or admin on any machine, you can own it. So with respect to design principles, they have described how they would stop information disclosure, ID, and how they would stop flip feng shui in a general sense, without yet respect to their implementation of page fusion. So for stopping information disclosure, they would first start by disabling detection of fusion via merge or unmerge events. And this is achieved by SB, that was described earlier, same behavior. For stopping flip feng shui, they need to disable the attacker's capability to control what physical page is chosen for backing merge pages. And this is done by RA, or randomized allocation. So let's jump right to it. In information disclosure, they described how they would actually implement stopping merge-based attacks by removing access to shared pages. The idea here is that any access will cause a trap and lead to an explicit copy via copy on access. The take home here is that it will prevent disclosure by disallowing the attacker the ability to detect fusion. And they call this share XOR fetch, or as the figure in the parenthetical shows. The idea here is that the attacker will no longer be able to detect what pages have been fused or unfused. It will only be able to detect at most what pages are candidates for fusion, which fits the earlier described threat model. Now, on the other side, stopping unmerge-based attacks. And so, as the idea can be seen, share XOR fetch doesn't actually stop unmerged detection. And how they actually enforce it on the unmerging side is via fake merging. And the idea of how that would be implemented is it would be removing all access permission and performing a copy on access for non-shared pages as well. Some have described a potential performance penalty, but that penalty is actually amortized because scanning is so spread out over the system naturally. Page fusion typically doesn't happen immediately and does take time, so that way to not take away time and resources away from the CPU and the rest of the machine. The premise here is that fake merging will help to ensure that unmerged pages look exactly the same as pages that were never candidates for fusion to begin with. That idea here is that all of the pages you're unable to detect which ones have been fused via share XOR fetch, and then unable to detect which ones have been unmerged via fake merging. And the combination of these two is what allows this design principle to, in an idea, implement same behavior. So next, now that we've covered both the merging and unmerging, we're going to move to the flip feng shui for stopping merge-based attacks with respect to that. The idea of how they stop merge-based attacks is they must allocate a new page on a merge event. Now, most allocators worth their salt are more efficient, and as such became more predictable for performance to not take away, again, the performance or the resources available to the user or to the rest of the machine. And so, randomized allocation must be done either system-wide or via the page fusion system itself. Now, if we decided to use the system-wide allocator, there would be basically non-trivial performance and usability implications with respect to fragmentation. Because then we're not only dealing with just page fusion, but we're changing how the entire system does it for user-level programs, kernel-level programs, which could definitely make the implications skyrocket past the point of this paper. So, as a result, the writers of this paper chose to use the page fusion system allocator, and they deduced that it will disallow the attacker to predict physical pages that will be used for backing fused pages. Next, we're going to talk a little bit about how VUsion does its implementation and how it adheres to those principles that we described earlier. Now, to implement share XOR fetch, they decided to use reserved bits. According to AMD and Intel manuals, this will generate a page fault on access. Well, that behavior by itself is not necessarily exactly what they want, but the idea is still there. And so how they're going to handle that page fault is by checking the bits first of the page table entry and then performing a copy on access if they're set in the right way to actually allow that to happen. To prevent a prefetch based attack, or they essentially try to attack via in a prefetch based style, they decided to also set the caching disabled bit in the page table entries. To enforce same behavior, they did the exact same thing. They use the reserved bits. And so it ensures that shared and unshared pages follow the same path to avoid timing attacks or detecting merge events. Now, there are some major differences between the VUsion implementation and KSM, and they are the follow. VUsion doesn't need the unstable tree, and to counteract bad performance with the fake merging, deferred freeing is actually done by queuing pages and then freeing them in the background. It's utilizing the fact that page fusion is not something that will stand up and start taking a large chunk of resources. It will have a lower priority than other things happening on the system. And so as such, it allows them this idea of being able to free things in the background without having to deal with problems with memory or any problems with taking resources from user or kernel level applications. Working set estimation. What they do here is they are going to assume that all pages are idle in the fusion round. This is when they are deciding whether or not the candidates will actually be fused. And those in the working set will trigger page fault regardless of merge location. Now, what ends up happening here in the VUsion implementation is that they get a large amount of page faults because of how that working set is currently set up. And so, to get around that and all of that wasted performance, VUsion estimates the working set and then doesn't initially consider it for fusion. Next thing to be talked about are transparent huge pages. Essentially, these are the huge pages that are not necessarily very normal and very common in the context of your Word document is not going to be a huge page. Your pictures or your videos are not going to be huge pages. But the, say, like the virtual disk for a virtual machine in VirtualBox or some kind of hypervisor, those are going to be very large, of course, depending on the size of your disk. But the idea here is there is a whole category of super large pages that Page Fusion would have to deal with. And so in the Linux kernel, there is the K-huge page D daemon for collapsing physical pages into huge pages. Their diction sort of implies that it or is a little hard to follow, and what happens underneath is the KSM will essentially break them up when sharing happens, and the daemon itself will take the physical pages and that are part of, like, say, that virtual disk that I described earlier, and will combine them all into one large huge page, or THP. And like discussed earlier, this is vulnerable to side channel attacks in detecting merge events in the original KSM implementation. So now they sort of have to rinse and repeat here with dealing with handling active and idle pages and how they can secure K huge page D in the same context of what they did for normal pages. And so to enforce same behavior, all pages must be considered normal or huge. Therefore, THPs will be broken down into normal pages before fusion. This enforces the same behavior principle that was described earlier, so that way they can't detect when pages have been fused or when they have not been fused. With respect to securing the daemon itself, pretty much it comes down to preventing the daemon from collapsing fake merged pages into THPs. And what this does is actually opens up a translation attack with respect to the pages that are next to the target page. And so the idea here is to only collapse if the surrounding pages are first fake, quote, unmerged before forming the large page. Basically, that comes down to the pages first need to be unmerged before the daemon will actually do anything with creating the huge page. So that way it enforces the same behavior regardless of whether or not those pages were initially part of a huge page or not. Next is a little bit of evaluation, and its comparison to the KSM is doing it on the Windows side is a lot more difficult with respect to trying to change the Windows kernel in order to make the changes and design principles be reflected inside of the Windows implementation. And so the coming evaluation is going to be able to answer the following questions. Does VUsion stop all attacks reviewed? How does performance compare? And how do the fusion rates compare? These are very important questions. If VUsion doesn't stop them, then why use it? If it is if it is terribly performing, then no one will want to use it. And if the fusion rates are abysmal compared to current implementations, then again, no one will want to use it. So let's get into how they actually created their benchmarks and their testbed. First, for a memory subsystem, they stressed it with Stream. It's a synthetic memory bandwidth benchmark. And then for some general purpose benchmarks, they use Spec CPU 2006 and Parsec. They use Postmark for a file system benchmark and Apache and Redis for server benchmarks. And all of these will be running on 4 VMs initially with a single virtual core and about 2 gigs of RAM. So let's get into it. Evaluation with respect to security. So first is the top right-hand figure. It shows the copy on write. You'll see the 2 peaks in KSM, which represent the side channels present in KSM. The bottom figure, the bottom right-hand side, shows no visible difference between unshared and shared pages. This is a representation of the same behavior. KSM, you see that there's not a whole lot of purple on the top hand side. So it is very obvious that someone could see when a page was merged and when a page was unmerged. However, in VUsion, it's more or less a mirror, which is the point, which then confirms that VUsion actually conforms to same behavior. Now, to test the enforcement of RA, randomized allocation, they recorded the offset of pages chosen for merge and fake merge in VUsion. Then a Kolmogorov-Smirnov goodness of fit test actually showed a p-value of 0.44. They were looking for about 0.5, which would be perfect uniform distribution. But at 0.44, it got very, very close. Therefore, randomized allocation is enforced. Next is performance with respect to the Stream benchmark, Spec, Parsec, Postmark, Apache, and then Redis and memory cached. With respect to the Stream benchmark, overhead by KSM or VUsion is below 1%. And that is shown in the bottom right-hand table that is labeled Performance of the Stream Benchmark. With respect to spec, KSM added a 2% overhead to the baseline, and then VUsion added 2.7% and 2.4% with huge pages. Based on Figure 7, performance overhead of spec CPU 2006, it's shown that VUsion enforces same behavior in randomized allocation with minimal performance overhead. There is a little bit, but it's honestly not a whole lot. With respect to parsec in the bottom left-hand side, labeled Figure 8, KSM added 1.7% performance overhead, where VUsion added 2.2 and is actually only 0.8% for bigger pages. Therefore, VUsion introduced low overhead and improvement in the large pages over KSM, which is obviously very good. With respect to postmark, KSM degrades by 1.5% and VUsion by 2.9%, but improves by 0.2% over KSM in THP in the huge pages. Therefore, VUsion can secure page fusion without performance penalty, which is, again, very good. With respect to Apache, KSM had a whopping 20% overhead, with VUsion adding 0.4% on top of that, an improvement of 12.7% with THP enhancements. That is huge. That is fantastic, especially with the very large rise of web-based attacks. With respect to Redis and Memcache, VUsion had unfortunately 5.3% worse than KSM, but only marginally different with THP enhancements. Overall, VUsion is performing just about on par as the KSM is, which is fantastic. Fusion rates. First, they started with idle VMs. VUsion, as seen by the top figure, VUsion converges to KSM, but is slower on the merging side. That's still pretty dang good. It's representing the fact that VUsion's performance with respect to fusion rates is pretty much negligibly different than the KSM, which is really good at showing a more secure solution is actually performing just as well as the current one, which makes it very easy to move. Scalability. And so with respect to scalability, they expanded to 16 virtual machines. And it is represented by Figure 11 there in the center. And they came out very similar to the normal testbed, but with the major change being in THP enhancement, where the fusion rate was enhanced to 61%. 61% better than the KSM. And then with respect to memory consumption during the Apache benchmark, KSM and VUsion are negligibly different. Last that was talked about in the paper was the related work with respect to attacks and defenses on page fusion before they came to their conclusion. And they are as follows. On the attack side, page fusion is also used in the flush plus reload attack. Page fusion is, like described earlier, able to create fingerprints or to make covert channels inside of the victim's system. And then the flip feng shui is used to physically massage to compromise crypto keys. A little bit of an extension on that last one described is using the Rowhammer exploit to flip bits inside of the keys that are stored on the machine as they are either being generated or handled in some way to actually create portions of um, pieces that are able to essentially become predicted in some way, shape, or form. They don't exactly change the implementation and software, but by changing what's happening in the hardware, they're able to essentially figure out the crypto keys as they are being used. And then with the making channels aspect of page fusion, they're either able to get them out in some way, shape, or form, or be able to watch them over the wire in some other fashion. With respect to defenses, page fusion is used against information disclosure in hexpads. They did not describe hexpads a whole lot in the paper, as it was very much so outside the scope of the purpose of this paper. The idea here is that anomaly detection system, hexpads, uses performance counters to detect suspicious behavior. So with respect to all that was talked about in this paper today, they came to this conclusion. Page fusion reduces memory pressure in modern cloud and consumer platforms. Unfortunately, the current approaches are weak with respect to information disclosure and control of physical memory. And so in the paper, they show the weaknesses are not fundamental and proposed a solution, VUsion. And then they were able to show that the new solution stops known attacks against page fusion. Thank you, everyone, for participating in this journey with us. I hope you guys are all staying safe and healthy and have a good semester.